Hello everyone, I'm Lida. I recently completed my PhD at the University of Calgary, and today I'm going to present our work, a trust model for human-machine interaction in virtual reality. This research was conducted under the supervision of Professor Yaoping. We will be going over introduction, method and results, and finally conclusion and future work. Virtual reality immerses human users to interact with a simulated world that is a machine and its operational environment. Such human-machine interaction characterize VR as a human-machine systems with three key elements of human, machine, and environment. Effective human-machine interaction in VR requires human trust in the machine to ensure overall system performance and usability. However, such trust remains elusive for real-time measurement. Besides, achieving such trust requires VR to be reliable, ensuring consistent performance from both human and machine sides. Trust in VR as an HMS can be measured qualitatively for giving categorical ratings or quantitatively to yield numeric values for analysis and is thus widely adopted in research, including this study. Qualitative and quantitative measurements can be subjective or objective. A practical approach to define and measure trust in VR is to develop a trust model by adopting one trust framework in HMS because there isn't any specific framework for VR. A trust framework is a basis for identifying components of the trust across the HMS elements as human, machine, and environment. As you can see in this table, most of the existing frameworks either doesn't consider all of the elements or be specified for one kind of machine. Meeting both the requirements is a three-layered framework which I use for proposing a trust model in this study. Derived from a framework, a trust model defines relevant metrics of the components within a scope. All a well-developed trust model should ideally align with a selected framework to identify relevant metrics and formulate the metrics for their objective measurement. However, there is a gap of lacking a trust model to meet these conditions, and there is an inadequate consideration of human and machine reliability for the trust model evaluation. Herein, the goal of this study is to fulfill this gap and propose a trust model aligning with the three-layered framework based on behavioral data in human-machine interaction within VR. So I proposed a trust model using the three-layered trust framework that covers three elements of HMS in layers as dispositional, situational, and learned. According to the proposed model, total trust is calculated as a weighted average of the three layers. I selected the metrics for formulations according to three considerations, as metrics should be measured objectively in real time or briefly assessed via questionnaire. The measurement could be taken in the scenario of one human user interacting with one machine, and an initial baseline of the trust model would be neutral. This table summarizes the metrics and definitions used in the proposed trust model. I mathematically formalized 9 metrics across the model's 3 layers. The resulting model includes gender and age for the dispositional layer, perceived workload, perceived risk, task difficulty, and organizational setting for the situational layer, machine performance, agreement state, and experience for the learn layer. I evaluated the proposed trust model using an abstractive and a quasi-practical use case. Both use cases involve the same task of haptically discriminating the shape of a surface in VR but different in their scenarios. As you can see in this figure, in the abstractive use case, a human participant um, is discriminating the shape of an invisible surface in VR using a haptic device. The invisible surface could have one of three shapes of valley, ridge, and flat. Each shape can be a matching or mismatching between the surface shape and force direction provided by the haptic device. Compared to the matching condition, the mismatching one was to disrupt the user's perception for relating to human reliability. The task had three steps as surface exploration, surface selection, and decision or recommendation. After the exploration, exploration, the participant had to select the shape they perceived. A recommendation about the shape of the surface was presented to them later. The recommendation could be correct or incorrect. The incorrect recommendations were used to manipulate machine performance, so the VR considered human and machine reliability concurrently. These tasks can have three orders as the surface exploration needed to precede the surface selection. Building upon the abstractive use case, the quasi-practical use case was flying a firefighting helicopter in VR to execute actions such as scooping water, dropping water, or flying. These actions correspond directly to traversing a valley, ridge, and flat shape. Human and machine reliability were manipulated same as the abstractive use case. For the evaluations, I conducted human studies to collect required data, then calculated the metrics and checked their normality and applied ANOVA and Bonferroni for the data analysis. For evaluating the proposed trust model, three task orders of the abstractive use case were used. I had 96 participants. I have four independent variables for four-way ANOVA as gender, order, surface, and recommendation. The trust layers and their metrics were dependent variables. Age is excluded as all participants were in the same age group, and gender and organizational setting are independent variables. All of the dependent variables were measured both objectively and subjectively except perceived workload, as there wasn't an established objective method to measure it. This table shows the main observation of a four-way ANOVA for results of the trust and its layers. The log data combined with the collected NASA TLX data form data 1. The data of NASA TLX and the data from the customized questionnaire became data 2, and the data collected solely from the predefined questionnaire was data 3. These ANOVA results show which factors or interactions made a significant difference in the trust layers and metrics. The post-hoc analysis revealed the correspondence between data 1 and subjective data as data 2 and 3, but subjective data often fail to capture interaction effects observed in data 1 calculated by the proposed trust model. Data 1 aligned with the metric agreement state, which shows user acceptance of machine recommendation, therefore validating the model's ability to reflect trust dynamics more accurately. Besides, the model enabled to trace metric-specific conditions to the trust. For example, for the trust in data 1, all main factors and two interactions made a significant difference, and we can see these effects come mostly from the learned layer. For evaluating the proposed trust model using the quasi-practical use case, order 1 was used as the effective order has been evaluated in the abstractive use case. I had 12 participants and I had two independent variables for two-way ANOVA, including surface and recommendation. I didn't consider gender and age because of the number of the participants. The trust layers and the metrics are dependent variables and were measured same as the abstractive use case. These tables show the main observation of a two-way ANOVA for data 1, 2, and 3 of the trust layers and metrics. As you can see, there is a discrepancy between data 1 and subjective data. This discrepancy was traced to the learned layer and its metrics as listed in these tables. Aligning with the results of the abstractive use case, the observation suggested that subjective data might miss subtle yet meaningful dynamics in the trust, whereas the data of the model demonstrated greater sensitivity in capturing the dynamics. Despite a small number of the participants, the proposed model pointed to a robustness of my model in capturing trust dynamics. As an important outcome of this study, I propose a three-layer trust model, which will be a tool to objectively measure human trust in machine to improve the interaction in VR to be intuitive. The model has been evaluated by concurrent consideration of human and machine reliability, which is missing in the literature. Potential applications of the model can be in designing adaptive and personalized VR, which enables VR to dynamically balance responsibilities and automation based on real-time trust assessment. The model can be used in training and simulations of safety-critical domains such as telesurgery, autonomous driving, and aviation. However, this model has some limitations which can be addressed in future work. For example, large number of participants or more metrics can be used for the evaluation. Different task or measurement methods and reliabilities can be also used for the evaluation. These are my references, and thank you for your attention.